Hi everyone, this is Jan Wilczek from thewolfsound.com, and in this video we are going to implement the variable speed replay algorithm. In the previous video we discussed the theory that stands behind the algorithm. In this one we are going to put the theory into practice. We are using Python, but of course this algorithm can be implemented using any programming language. I am going to implement it in two ways. The first one is going to be the direct implementation of the scheme that was described in the previous video. The other way is going to be only one line long and is going to be presented at the end of the video, showing that somehow the easier solutions are even more optimal. We start out by writing the main function. We put the usual condition here. Then we define our input parameters. These parameters could be passed in as command line arguments, but we are going to have them fixed in order to simplify the algorithm. We have our test file piano, and we define the n, namely the numerator of the v timescale parameter, and m, the denominator. Let's first set n to 2 and m to 1. And please be reminded that v is equal n over m. Now, since we are going to use the top-down approach, we firstly have to pre-process the file. Then we process it using the variable speed replay algorithm. The process frame Crude parameter is a function we are going to use to process each frame of the audio. And then at the end we are going to play it out. Okay, so let's get into it and program all the elements we've put here. The first thing we are going to do is we are going to read and preprocess file. For that, we need to import the read function that will enable us to read the WAV file. Firstly, read the file, then we extract only the first channel because our audio file may be multi-channel, but we only want to take care of the first channel. Of course, it can be extended to more channels, but we don't have to do it right now. Then we normalize our data by dividing all the samples through the maximum sample. So we are sure that our signal is in the range from -1 to 1. I am using NumPy here, so we have to import it. once we've done it, we're ready to return our data. We are returning the sample rate and the data itself. Okay, so we're done with the first part of the task, namely the reading and preprocessing of the data. Now we want to implement the actual variable speed replay algorithm. Let's first define our main entry function, and what do we have here? Samples, sample rate, m, n, and process frame method. Okay, first let us check whether the n over m is not equal to 1, because if it is, we can just return the samples that we received. Okay, if it's not, we have to define the output variable that will append our transformed samples to. Alright. Okay, now we're ready to write our main loop. We are going to iterate from 0 to length of the samples, but we're going to jump every frame length samples. Now we have to determine what is the end of the frame we are going to process, because we don't want to extend beyond the samples vector. So this one is going to be the minimum value between I plus frame length and the length of the samples. Now we are actually processing the samples, which we are doing by calling the process frame method, and we are passing it samples from I to end, then the sample rate, the m and n. Finally, we are appending the samples to our output vector, and at the end we are returning the output. Okay, so let us now write the process frame method, which in our example is initially process frame crude. As mentioned before, the process frame crude method is suboptimal, but it shows exactly step by step how to process the samples in the algorithm. Okay, so what do we have to do here? First, we have to upsample the frame by a factor of m. Then we have to filter it. You will see in a second why am I passing fs over 2. And then we are downsampling. By a factor of n. And then we return the processed frame. Okay, so let's first do the upsampling. Upsampling means here inserting m-1 zeros between every sample. So first we can define a list m-1 zeros, which is exactly m-1 zeros. And then for each samples we insert m-1 zeros. We start with the first sample because that's the syntax of the NumPy insert function. Let me just show you how it works. Okay, first we determine the sample ID that we want to insert in, because with each iteration we're changing the frame variable, what means that the indices also change. So we have to be really careful in order to have the right index each time. And this one is going to be equal to I-1 times m plus 1. And why is that? Because we change each sample into a frame of m samples. So after I-1 processed samples, we have to skip all the frames that we created. For instance, for the first sample, the I-1 is going to be 0 because I is going to be equal to 1. So the next sample ID will be just 1, and it's perfect because we want to insert m-1 samples before the first sample, which is after the 0 sample. So we do something like this. On peut insert and frame, and now we have to pass in the index, and then we have to pass the values we are going to insert. Okay, and we are done. The second thing we are going to do is we are going to write the filter frame function. And now you see why I used the fs over 2 before, because we only need here the Nyquist frequency. Okay, first we have to define the order of our filter. Let's set it to 5. Then we need to determine the cutoff frequency of our filter. As you may recall, we are filtering our signal 2 times. But instead of doing that, we can only filter it using the low-pass filter with the lower cutoff frequency. Which means that you can write cutoff frequency is the minimum value between the Nyquist frequency over m and Nyquist frequency over n. This formula comes from derivations which you could see in the theoretic video. Now we have to normalize this frequency to the range from 0 to 1, where 0 means 0 Hz and 1 means Nyquist frequency. And now we are ready to create our filter. For that, we need to import butter function from the SciPy signal module, the L filter function for filtering our signal. Okay, so now we can write BA is butter, order, then normalized cutoff, and then we have to write what time it is. This B type is low, and then we have to write analog is fast because we want to create a digital filter. and then we return the filtered signal. It's as easy as that. Okay, so we're ready to write our downsample function. Oh, I just noticed a mistake here. We of course need to have upsampled here and filtered here. Okay, let's now write the downsample function. And this one is going to be the easiest one of them all, because we just have to return every nth sample. We can do it by list comprehension. We return frame of I for I in range 0 to length frame if I modulo n is equal to 0. Okay, we are almost done with our algorithm. We only have to write the play samples function, and for that we need to import the sound device. We can also have the parameter volume here, which I will set to 1.0, and we're ready to play out the samples. We multiply the samples by volume, and we set sample rate to sample rate. And then we have to wait in order not to close the program before it finishes playing our sound. Okay, so after writing the whole code, we are going to launch it. We have the file piano, and let me just play it out to you how it's in the original. Okay, it's a nice piano sound. So now what we can do, we can fasten it 2 times. Okay, so what happened was that it took quite a while to process. Therefore, we are going to employ a much simpler method and much more efficient. And let's call it process frame smart. Let's insert it here, and for that I'm going to write it in just 1 line. We don't need the sample rate anymore. Okay, so this function is going to be really simple, just 1 line long. We will resample the frame to a new length, which has to be integer, and the length of the new frame is the length of the old frame divided by v, which, as you recall, is n over m. Right now, the only thing we have to do is we have to import the resample utility from the SciPy signal. Okay, so let's hear how does it sound. Okay, as you hear, it sounds exactly the same as the previous one, but what is more, the result we got was computed a lot faster than our Crude implementation. So let's now see what can we do here. Okay, we can maybe slow it down 2 times. Okay, and we can maybe fasten it up 3 times. Or maybe even 10 times. As you may hear, there are some artifacts to the sound, but nevertheless, the overall impression is really interesting. And as you can see, we can implement this algorithm relatively simple when we have some sort of resampling utility. If you want to see the full code, I've linked to it in the description down below. It contains some command line features so that you can use it from command line with an arbitrary file without hard coding it in Python. Lastly, I would like to encourage you to subscribe to this channel and hit the thumbs up. I hope you enjoyed the video and see you in the next one.